right, so at this point in our lecture, we've talked a lot about isomers of alkanes, we've talked about isomers of alkenes, we've talked about constitutional isomers versus stereoisomers. We're going to add another layer to that discussion. All right, so let's go back and review constitutional versus stereoisomers. Constitutional isomers, if you remember, have these same molecular formulas. So these two examples down below both have the molecular formula C4H10. However, the arrangement of those atoms is different spatially, which makes them isomers of each other. Because the arrangement is different, they have a different name. So here we see butane, that's our longest chain isomer. And here we have 2-methylpropane. So again, different name, constitutional isomers, same molecular formula. With stereoisomers, you have the same molecular formula just like you would with a constitutional isomer, and you still have a different arrangement of atoms in space. However, it's the same order of these atoms. This is where we have our cis-trans forms of stereoisomers. So again, the double bond here is in the same place. It's coming off of the second carbon for both of these. So if we were to name these guys, they would both be 2-butene. The differences are the groups on the same side of the double bond, or are they on different sides of the double bond? So that's where that different arrangement in space comes from. So again, as a reminder, because I know you've done this before, this would be trans 2-butene, and this would be cis 2-butene. So the difference between these is that their arrangement in space is the same, and it does have the same order of atoms. However, the grouping around that double bond is different. All right, so what's new? Stereoisomers can be separated into two further categories. There are enantiomers, which are mirror images of each other, and there are diastereomers, which are not mirror images of each other. So this is where it gets a little weird. We're going to go to the next slide, take some notes on it, and see some real-life examples. All right, before we can go into enantiomers, we're going to have to talk about this idea of a mirror image. All right, so the example that you're seeing on your screen is a hand. We're pretending that there's a mirror sitting right in front of the hand. Whatever is closest to the mirror is going to be the first thing that comes up in your mirror image. So for example, my pinky is closest to the mirror. So in the mirror image, that is closest as well. If you were to look at your hands and pretend that there was a mirror here, pretend that there's a mirror right here, this is what your mirror image would look like. They are mirror images of one another. That's what we mean by a mirror image. To say that they are not superimposable is a little more difficult, and it's going to be a little difficult to explain on video, but we'll work on this in class as well. When I say they are not superimposable, what I mean is you cannot take them both palms towards you, okay, and lay them on top of each other and have them line up perfectly. They just don't do that, okay? In order for them to line up perfectly, I would have to turn them palm to palm. That is not superimposable. They would have to be able to lie on top of each other and match up perfectly to be superimposable, and hands are not superimposable. They are not both facing the same direction when they are lined up. Okay, I have one that is palm towards you and one that is the back of the hand towards you. That's the only way I can get them to line up. I cannot get them to line up with both my palms facing myself. And that's what we mean by mirror images and something being non-superimposable. Socks, unless you're one of those people who buys the left and right footed socks, which power to you, are superimposable. If I were to line up the mirror image and I put the heel closest to the mirror image would have the heel closest. So these are mirror images. However, there's no right and left. You would be able to take those socks and lay them on top of each other and do what we call superimpose those socks. So socks are mirror images that are superimposable. All right, so let's take this back to chemistry. So enantiomers are mirror images, meaning you put one up, you will see the other's mirror image. Whatever is closest to the mirror is going to be closest to the mirror in the mirror image. They're not superimposable, so think about your hands. You can't line them up in the same direction. They're going to lack symmetry. So an example of this would be these two structures. Here's my mirror. The hydroxyl group is closest to the mirror in this structure. hydroxyl group is closest to the mirror. That is a mirror image. Hydrogens are out. Notice that this is the same arrangement of atoms. Okay, carbon 1 is CH3, carbon 2 has a hydroxyl group, carbon 3 has a bromine, and this is the same for both of these guys. On the third carbon down, my hydrogen is closest. I see that in the mirror image. My bromine is the furthest from the mirror, and we also see that in its mirror image. So that's what we mean by mirror images. These two enantiomers, and it's really hard to see this in 2D, and we will work with this in 3D in class, but these two enantiomers would not be considered superimposable. You would not be able to put these two on top of each other and have them line up perfectly. Diastereomers are cis-trans forms, as we talked about before, but they're not mirror images of each other. So here we see atoms in the same basic arrangement in space. You have an aldehyde at the top. On carbon 2, you have a hydroxyl, and in this case, look at this. The hydroxyl group on carbon 2 is a mirror image. We see the same on carbon number 3, but when we get to carbon number 4, we expect the hydroxyl to be closest to the mirror, and so our mirror image should have the hydroxyl on this side as well, but it does not. Okay, so all of a sudden we've disrupted that mirror image. These two molecules are not mirror images of each other and therefore would be considered different molecules.